Just a quick introduction to dot products. Okay, dot product of V and W, where V is A1 through AN, W is B1 through BN. If these are column vectors, then you take the transpose of V, multiply it by the B vector, giving you just A1 B1 plus A2 B2 up through AN BN. So that'll be our definition of dot product. In R2 or R3, we can show that V dot W equals the magnitude of V times the magnitude of W times the cosine of theta, where theta is the angle between the two vectors, and the magnitude of any vector is the square root of its dot product with itself. And that dot product will always be positive. If I had A1 through AN here and A1 through AN here, so I was doing V dot V, I'd end up with A1 squared plus A2 squared and so forth. They'd all be squared, I'd be adding them, I'd get something positive, unless of course V was a zero vector, which would be the only way I could get a zero for the dot product. Now there's a property of the dot product there, the positive definite property that I mentioned over here. So anyhow, that's what we've got. And you can prove this in R2 and R3, where you have vectors, and any two vectors form a plane within R3. Any two vectors in R2 are automatically in a plane, so you get a triangle, okay, with an angle theta here, and the law of cosines applies to this triangle. Okay, well, magnitude of V is the length of this, magnitude of W is the length of this, and it follows by the law of cosines that, well, the square of this equals the square of this plus the square of this minus this times cosine theta. Started to point the wrong place, had to stop and correct myself, okay? And that's just magnitude of V squared plus magnitude of W squared minus 2 magnitude of V, magnitude of W times cosine theta. If you write out V and W in terms of A1, A2, B1, B2, and so forth, you can actually write that out, except for the cosine theta, in terms of those symbols, A1, A2, A3, B1, B2, B3. It tells you then that the cosine theta equals this, and again, that's just an expression that can be written out in terms of your A1 through AN, or B1 through BN, and B1 through BN. And that's going to equal this, which can also be written out in the symbols A1 through AN and B1 through BN. And notice that I've left R2 and R3. Okay? If n is equal to 2 or 3, yes, it applies to R3 or R2. No reason not to apply it to Rn for any n, any positive integer n. And you can then write this out and do a little bit of arithmetic, a little bit of algebra, and show that this expression will equal this expression. Okay, so that gives us dot product. The dot product has some properties. Okay, it's commutative. Doesn't matter in which order you do the dot product, and that should be obvious. You just write this out and then replace the A's with B's and B's with A's. That CV dot W equals V dot CW equals C times V dot W. And again, very obvious property that you just write it out in symbols and show that it's so. That we have a distributive law that V dot W1 plus W2 equals V dot W1 plus V dot W2. And also, very important, that V dot V is never less than 0, and it's only equal to 0 if V is the 0 vector, something I mentioned in the context of this. Okay? So that's it. Now, there's a lot we can do with dot products. An inner product is going to be any way of combining two vectors that satisfies rules like this. We won't use dot for the inner product. For the inner product, we would say V comma W is the inner product. And this is just a rule for combining V and W. That V combined with W equals W combined with V. That CV W equals C times V W. That V W1 plus W2 equals V W1 plus V W2 and VV greater than or equal to 0 n equal if and only if V is a zero vector. Now there are lots of inner products. One inner product, it's easy to verify, is in the space of functions, integrable functions. Okay, the inner product of fg could be the integral over some interval, and I'll just say integral from a to b of f times g, okay, with respect to whatever the variable is. Okay, can we verify these products? Well, does fg equal gf? Is the integral of f times g equal the integral of g times f? Certainly by commutativity of multiplication. If I multiply f by c, do I get c times the integral? Well, yeah. Constant multiple property of integration. If I multiply f times g1 plus g2, I get the integral of f times the quantity g1 plus g2, which separates into the integral of f times g1 plus the integral of f times g2. And the only way f could be 0, since the inner product ff would be just the integral of f squared, the only way the integral of f squared can be 0 is if f is everywhere 0. Okay, now that's for integrable functions. And, actually, if the functions are a little weird, we're at discrete points, discrete values of the variable, f takes a non-zero value, but only for a single point. Your integral would still be 0, and your f would not be identically 0, but that kind of violates the conditions on f for which the inner product applies. So I just mentioned that as something to think about. Okay, so there's an inner product that doesn't look anything like a dot product. You could even use this to find the angle between two functions, whatever that might mean, and it does have significant interpretation in many cases. I'll also mention that the space of all integrable functions with certain restrictions can be spanned by an infinite set of sine or cosine functions or other infinite sets of functions. So you have like an infinite basis for what turns out to be an infinite dimension of space. Just something to chew on. Don't have to worry about it right now. Okay, so there we have kind of an overview of inner product, and we want to talk about inner product spaces, vector spaces on which you have defined an inner product. And we can see from this example that vector spaces of which you've defined an inner product can be pretty general things that don't look anything like arrows. Okay.